For reasons I explained last time, there's only a very short list of possible S's. S is CP2 or CP1 times CP1, or one of these Del Pezzo surfaces, which are just CP2s with a few points blown up, no more than 8 points blown up. And they all have the property that pi1 of S is 0. And therefore, we can't break SU5 to the standard model by Wilson lines. The only way we can break SU5 to the standard model is to turn on a hypercharged gauge field. And it can't be flat because pi1 is 0. So we're going to take the hypercharged U1 gauge field to be non-zero. Now, that's playing with fire, because when we do that, there's a danger of shifting the spectrum in a way we don't like. You see, inside SU5, our hypercharged gauge field looks something like this. And it has to be topologically interesting, because Maxwell's equations force that upon us. We have to solve Maxwell's equations, and you can prove that if the solution is topologically trivial, f will actually be 0. So this is a topologically interesting solution of Maxwell's equations, and it could contribute to index theory. What it could do that we wouldn't like, well, there aren't going to be any massless x and y gauge bosons, because we've broken the SU5 symmetry to the standard model. But there could be massless chiral supermultiplets with the quantum numbers of x and y under the standard model, and that would be just as bad. So massless chiral superfields with quantum numbers 3, 2, or 3 bar 2 of standard model, SU3 times SU2, come from solutions of the Dirac equation that are coupled to this background U1 flux. So we essentially look at the Dirac operator, but the Dirac in this situation turns into the D-bar operator of a complex manifold. S is a complex manifold, and well, supersymmetry makes sure that it's really the D-bar operator we run into. So the condition we need, the zero modes come from what's called the cohomology of S with values in the line bundle L, where L is whatever line bundle the fields we're interested in transform in. And if the 3 2's transform in S, then the 3 bar 2's transform in the opposite line. The 3 bar 2's have the opposite U1 charge from the 3 2's, so for them the line bundle L is replaced by L inverse. So we want these to be 0. For all I equals 0, 1, or 2. It turns out that that condition determines what L has to be. Up to a diffeomorphism of S, there's only one L that works. for example, if S is CP1 times CP1, then L is characterized by how many units of magnetic flux there are on the two CP1s. And the flux has to be 1 minus 1, or minus 1, 1. Or else you'll run into a bad zero mode for one field or another. So these two cases are essentially equivalent up to exchanging the two CP1s. So in that sense, there's only one model. You can work it out for all the Del Pezzos, but you find that there's only one L that works up to a diffeomorphism of the Del Pezzo. So that's kind of nice. You have a non-trivial solution of Maxwell's equations. Right. But, of course, you need Dirac quantization on the flux.
So we know it's U1 hypercharge, so what is the difference between different line bundles?
Well, when we solve the equation, let's discuss the concrete case of CP1 times CP1. According to Dirac, the magnetic flux will have to be 2 pi times an integer on each CP1. So the solutions we can use are classified by a pair of integers, n and m. Then we have to solve the Dirac equation, and we find out we don't like the answer except if we take 1 minus 1 or minus 1, 1.
So these different solutions of U1 hypercharge are different solutions?
The choice of line bundle is equivalent to the choice of the fluxes n and m in the solution of Maxwell's equation. Any other questions? So that's kind of nice because S was not completely unique, but there was a very short list of S's, and for each S there's only one SU5 breaking scheme. So it's more constrained than you might have thought.
So these are like having manifolds at the center of these CP1s?
Yes. The center isn't in the space, but yes. That's right. The field on each two-sphere looks like a magnetic monopole field restricted to a sphere around the monopole. So the next thing which we'll discuss is doublet-triplet splitting. So remember the basic setup. We have a 4-manifold S where the gut model lives. And each 5 or 5 bar or 10 or 10 bar is supported on a 2-manifold. And here I've drawn, I'm expressing that poorly. The 6-dimensional hypermultiplets are supported on 2 manifolds. And hypermultiplets are real, so if there's a 5, there's also a 5 bar. To reduce to 4 dimensions, you have to solve the Dirac equation on the 2-manifold. And depending on the flux on the 2-manifold, the index problem might materialize 4-dimensional 5s or 5 bars. So here, I want to assume that there's a hypermultiplet on C, which is, let's say, 5 plus 5 bar. And we get 4-dimensional chiral multiplets as usual from 0 modes on C. And these are 0 modes on C of the Dirac operator. So the Dirac operator with no flux has no solutions, but if we turn on flux on a 2-sphere, then we get a solution. So, okay. We have the same thing we just talked about, But now we're solving a Dirac equation on C instead of S. So different things can happen to us depending on what this two-sphere is. For example, even if on S there was non-trivial flux, on C it might be 0. That's one thing that can happen. But another thing that can happen to us is that we shouldn't assume the eigenvalues add up to 0. And the reason we shouldn't is that C arises from an intersection. Well, okay. You could argue that even up here we shouldn't have assumed they added up to 0 because the gauge group was U5 rather than SU5. But even if we've gotten rid of that U1 somehow, there's another U1 in the game. Because C actually, remember, arises where S intersects another brane. And that brane has its own U1 under which this 5 is charged. So we're allowed to shift these eigenvalues. And I want to shift them like this. Oh, sorry. Right. No, I want to shift them like this. I've chosen the shifts so that there's no shift for color triplets, but there is for Higgs bosons. And therefore, if we pick the right value of A, we get one zero mode for the Higgs doublet and none for the triplets. So what's going on is that first we decided how we were going to break SU5. And then there are various two manifolds in S on which hypermultiplets in the 5 representation are supported. And for the ones that are going to end up being interpreted as standard model quarks and leptons, we do not want any doublet-triplet splitting. So those are two manifolds on which A is 0. On the other hand, there should be another two manifold where we do get a Higgs boson, either a Higgs up or a Higgs down. And on those, we want A to be non-zero. In fact, we want it to look like this. And A will be either -1 or 1, depending on whether we want the 0 mode to be part of a 5 or a 5 bar. So we actually need 3 of these surfaces. Oh, that's bad. Oh, no, I dropped the ones we're finished with, so I think we can leave them on the floor. Okay. We need 3 of these surfaces, at least. One will support Higgs up, one supports Higgs down, and one is going to support 5 bars of quarks and leptons. So to get 5 bars of quarks and leptons, the eigenvalue should be maybe -3 for all fields. The minus sign just will give us 5 bar instead of 5. So the number of generations, well, we have to get the 10s as well, but the number of 5 bars, quarks and leptons, came from the flux on that sphere. But there are 2 more of these guys. One supports Higgs up and one supports Higgs down. And on them, the flux has to look like this, where 5A is either 1 or -1. By the way, you might be slightly nervous about the fact that in that case, A is 1/5 or -1/5. So Beasley, Heckman, and Waffe go into a long story about fractions. But all it actually means is that as long as all your Dirac equations make sense, the picture makes sense. So as long as we get an integer flux acting on every physical field, the model makes sense. So some of the formulas, so A is a 5th, and that's okay. You might notice that if A is a 5th, then these guys up here actually had a charge of 5A, so they also have integer charge. Or they're coupled to an integer flux. So anyway, the quick answer is you don't have to worry about any fractions. You can read a longer answer in the paper if you want to, but okay. Now, Waffe, Beasley, and Heckman also show that you could modify this story a little bit to get Higgs up and Higgs down from the same curve. I thought it was less elegant, but it also has a drawback they point out, which is that there's a mu problem. Here, there's no way to get a gut scale mu because these are different curves. So any mechanism for generating mu ends up being highly suppressed, which they want to use as the method of solving the mu problem, explaining why mu is at the electroweak scale. They definitely have natural suppression of mu, but whether To me, it's hard to make sense of the question of whether it lands at the electroweak scale without understanding how to generate the electroweak scale. So they're producing a small mu, but since there isn't a natural mechanism of supersymmetry breaking and generating the weak scale into which mu is integrated, it's hard to say whether they solve the mu problem.
The three families of 5 bars come out because there's 3 solutions to the graph equation.
That's right.
So is there anything that distinguishes those 3 families?
They have different wave functions, so they won't get the same masses. What'll happen, you see, their masses are going to come from some intersections like we discussed yesterday. So we still have to discuss it for the Yukawa couplings that give down. For the 5, 10, 10, we haven't discussed it yet, but I guess the charged leptons get masses from the 5 bar 10 that we did discuss. So they arise from certain intersections. But each intersection involves one point. And one linear combination of the 3 wave functions is non-zero at that point. So the mechanism we described yesterday would only give, for each intersection, mass to one linear combination of charged leptons. So the picture has to be complicated enough to contain 3 of those intersections. Well, if there only are 2, we'd get a massless charged lepton in this approximation, and we'd have to generate the electron mass from some kind of radiative correction.
Isn't it true this really makes it very hard to understand why mu's at the weak scale? I don't think any of all that was popular ideas for doing that either invoke the addition of some extra singlet or something, which gets it out near the weak scale.
Yes.
Couples H up and H down.
Yes.
That Yukawa coupling will be exponentially suppressed. So that can be incorporated. Or no, the Yukawa coupling will be exponentially small.
No, but you can have another. You can have another brain split.
But it doesn't matter. If H up and H down are separated, there's no big Yukawa coupling between them. And also, and the other ideas are like that mu comes from the same source. It's a supersymmetry breaking effect. But if the matter fields are sitting in the same place, then there's no suppression for the sort of Q dagger Q type soft terms. But there will be the same exponential suppression for the H up H down term.
Well, I think it's a cause for concern that if you suppress mu in ways that's unrelated or not obviously related to supersymmetry breaking. That's actually what I tried to say. Okay, well, the most pressing thing which we haven't described is how to get the 5, 10, 10 Yukawa couplings. Remember that the 5 bar 10 came from, well, we had 2 kinds of special 2 surfaces. One was where we meet another brane, and the other was where we meet an orientifold plane. As I explained yesterday, you can get a 5 or a 5 bar, well, I just reminded you, on this guy, and a 10 or 10 bar on the other guy. There's something I didn't want to draw yesterday because it was too messy, but I actually will draw it now. This guy is not invariant under the orientifold reflection, so it has a mirror image there. So it's actually a triple intersection on S that gives us the Yukawa coupling. There's a 2 surface that supports a 10. There's a 2 surface that supports a 5. And there's the mirror image of the 2 surface that supports a 5. And of course, the mirror image is just as good as the original guy. So that again is a 2 surface that supports a 5. Only they're equivalent 5s under the orientifolding. So to get this Yukawa coupling, S contained a triple intersection. I didn't exactly draw this picture yesterday. When I drew the triple intersection, it was a simplified version, which I could remind you of. I drew a one-dimensional slice. Here's the orientifold, here's S, here's its mirror image. Then the other guy we called T, and T has a mirror image. So a whole lot of things are all meeting at one point. Well, in the slice it looks unnatural. Even here it looks a little bit unnatural at first, because in 4 dimensions, 3 two-manifolds normally wouldn't meet unless there's a reason. Here the two manifolds are the one that supports a 10, the one that supports a 5, and the mirror image of the guy that supports a 5. However, you can see that they all will meet at a point, because granted that these two meet somewhere, the mirror image of this guy, that's a point that's invariant under the orientifolding. So the mirror image automatically contains the same point. So this is a case where it is natural for 3 guys to meet at one point, even though counting dimensions would have told you otherwise. Now, as a preview, I'll draw the picture that will lead to the 5, 10, 10, but in perturbative string theory, we'd have trouble making sense of the picture. You could just guess the picture as follows. Inside S, we decided that matter was supported on 2 surfaces, and we got a Yukawa coupling from 3 two surfaces meeting. So we got 5 bar, 10, with 2 surfaces of type 5 or 5 bar and 1 of type 10. So if we just exchange the 2 types of 2 surface, we'll get the other kind of Yukawa coupling. So I'll just turn every solid line into a dotted line, and every dotted line into a solid line. So now I've got two surfaces supporting 10s and 1 supporting a 5. Okay. So these are all intersections with 4 manifolds that go off somewhere. So the picture that gives the other kind of Yukawa coupling, roughly speaking, is simply that instead of an orientifold plane meeting 2 branes, we have 2 orientifold planes meeting 1 brane. The only trouble is that in perturbative string theory, you can't make 2 orientifold planes meet a brane, or even each other. Orientifold planes don't meet in perturbative string theory. So that's why we have to learn F theory. At least in the way I'm approaching it. The biggest reason we have to learn F theory is to make sense of how to get this Yukawa coupling. But we're going to keep it kind of painless. We won't have to learn too much F theory, just a little bit. We will kill the, well, I started to say that we'll kill the global U1. Well, you see, we discovered the U1s near this picture. But as I warned you, for a variety of reasons that I mentioned both in the morning and the afternoon, some U1s that you see near this intersection might not be symmetries of the whole picture. Now the opposite's going to happen, but the U1s we found were U1 symmetries of the 5 bar 10 Yukawa coupling. Now the opposite's going to happen here. We'll see some U1 symmetries which will be symmetries of the 5, 10, 10. Now, of course, in a picture that has both Yukawa couplings, it won't have any U1 symmetries that don't allow them both, which will mean that some of the U1 symmetries we see locally in either this or maybe both are actually not valid globally, for which I described 2 possible mechanisms in the morning and 1 in the afternoon. And I don't claim it was a complete list. So it's very convenient here that you see U1 symmetries locally that help constrain things, but and help analyze things, as you'll see. But they may or may not be valid globally. Anyway, now we're going to do a little bit of F theory. So, well, I draw the same picture we had at the beginning yesterday. This is the z-plane, which is normal to a D7 brane. Well, let's say normal to n D7s. And the D7s are here. And tau, as I explained yesterday, looks like near z equals 0, looks like minus in log z over z0. For some z0, it has a monodromy, tau going to tau plus 2 pi n, in going around a circle. the change in tau in going around the circle is tau going to tau plus 2 pi n. Sorry. As usually normalized, the change in tau is n. Okay. Now, it's convenient to absorb the monodromies. To find a mathematical formalism, we can write down things that don't have any monodromies, but you could then compute the things that do have monodromies if you want to. So, in other words, it's convenient to work with single-valued functions. And, for example, an obvious way to do that would be to just take e to the 2 pi I tau. That doesn't have any monodromies. The trouble with that is that when we get to strong coupling, there will not just be D7 branes, but there also will be PQ7 branes. And there will be more general monodromies, not tau going to tau plus n, but tau going to a tau plus b over c tau plus d. We didn't need those more general monodromies yesterday, but to get the 5, 10, 10 Yukawa coupling, we will. We would, if we express it in terms of monodromies. We'd run into non-commutative monodromies. And although it's elementary to write a monodromy invariant function for just this operation, when we start having non-abelian monodromies, we'd have to introduce complicated transcendental functions, like the J function. There's a more convenient way to do it, actually, which is to treat tau somewhat implicitly. A natural interpretation of tau is to take a torus, or to be fancy, a Riemann surface of genus 1, and you can always describe the complex structure of a torus by taking a parallelogram in the complex plane with vertices at 0, 1, tau, and 1 plus tau. So then identifying opposite sides of that parallelogram gives you a torus that's said to have a tau parameter of tau. And the reason this is a natural interpretation is that if we make this kind of transformation, we actually get an equivalent torus. There's a somewhat more intrinsic way to describe it. You have any torus, what I'll call C, I think. Oh, sorry. We used that yesterday, so I'll call it sigma. Then you pick what are called A cycles and B cycles. And then you pick a holomorphic differential. Omega. In this picture, with this being the x-plane, the u-plane, let's call it, omega could be simply du. The A cycle could be the path from 0 to 1, and the B cycle could be the path from 0 to tau. And then you see that the integral over A of omega is 1, and the integral of B over omega is tau. And that facts suggests that we could define tau as the integral over the B cycle of omega divided by the integral over the A cycle of omega. Now, one nice thing is that it didn't matter what omega we picked. Any two omegas are multiples of each other in the case of genus 1, and the constant would cancel out because we took a ratio. Another fact is that there's a lot of arbitrariness in picking the A and B cycles, but the arbitrariness you discover after a little bit acts on tau like an SL2Z transformation. Tau going to A tau plus B over C tau plus D. So the most natural SL2Z invariant object is a Riemann surface of genus 1 whose tau parameter is tau. Just to recapitulate some of what I said, if you give me tau, I just construct the Riemann surface of genus 1 by making this little parallelogram. and identifying the opposite sides. That gives a Riemann surface of genus 1 that was determined by tau. And two different taus, which are equivalent by SL2Z, give equivalent Riemann surfaces. So the natural modular invariant thing to talk about is the Riemann surface. And another useful thing to know is that a Riemann surface of genus 1 can be described by an equation. The equation we can take to have the form y squared equals a cubed, x cubed plus ax plus b, where we also need to include a point at infinity, a point where x and y are infinity, to get a compact Riemann surface. Now, describing it in this form, okay. This isn't a completely gauge invariant description for the following reason. If we take a to c squared a and b to, maybe it's c cubed, b to, well, x go to cx, c squared x, y goes to c cubed y, and some powers of c for a and b, which we'll figure out in a second. B would be c to the 6th, and a is c to the 4th. So there is a rescaling of a and b that gives us an equivalent Riemann surface. So there is a gauge invariance in this description, but it's much more elementary than SL2Z. The reason it's convenient to work this way is that although this description isn't completely canonical, the indeterminacy is elementary. Whereas in the other description by tau, SL2Z is a very SL2Z is a very slippery thing to work with. So a single Riemann surface would be given by an equation like this, where a and b are simply complex constants. But now we're going to become F theorists. We're not going to look at a single Riemann surface. We're going to look at a Riemann surface that depends on z, where z is our coordinate in this picture. So remember, as I said at the beginning yesterday, the idea behind F theory is that the tau parameter of type 2b is not constant. Supersymmetry doesn't require it to be constant. And I even wrote an example. Here's an example of a completely supersymmetric formula for a tau parameter, which is the correct behavior of tau near a D7 brane, or actually n D7 branes. So we have in that formula a tau parameter for every z. So we have a Riemann surface of genus 1 for every z, and that just means that a and b are functions of z. So now we're F theorists. We just write down this equation where a and b depend on z. Now we've introduced a complex dimension, a complex manifold of one higher dimension than the physical manifold. The physical type 2b manifold was parameterized by z, but now we've introduced x and y, but they obey one equation, so we're in complex dimension 2. But this complex dimension 2 manifold that we've introduced is just a convenience for describing how tau depends on z. However, that 2 torus can get a more physical meaning. If you compactify type 2b on a circle, that's the same as M theory on a 2 torus. And the 2 torus is the one whose tau parameter is tau. So in F theory, so we could have F theory, as I've said it so far, and we're on R17. There's what people call F theory. Let's say that this equation describes something that we'll call M, where A and B now are functions of Z. So I was asked yesterday, don't people talk about a 12 manifold? Well, this is the 12 manifold. The 12 manifold is what you get if you take space-time and add an extra complex dimension to encode in a convenient fashion the spatial dependence of tau. Now, we could compactify it in a circle. So we're on R16 times a circle times M. So remember, what that really means is that we're on type 2b on R16 times a circle times the Z plane. But because there's a funny dependence of tau on Z, we've introduced this form manifold M to encode how tau depends on Z. But F theory on a circle is the same as M theory on a 2 torus. So it'll be R16. Well, I'll first write a naive version. The naive version is R16 times the Z plane times T2. But T2 is vague. A 2 torus is supposed to have a metric, and in particular a tau parameter, which contains less information. And what is tau? Well, tau is a function of Z. How do we make tau a function of Z? We build the form manifold M. So the correct version of this is really that F theory on R16 times a circle times M, and that's a somewhat symbolic description because the 2 torus part of M is just a way to encode some information, but it's not really there as a space. That's equivalent to M theory on R16 times M, where now M is a real space. So the meaning of M is a little bit abstract in F theory, but if you compactify in a circle, it becomes completely concrete in M theory. In M theory, there's a metric, and in particular, the T2 has not just a complex structure, but an area. And if you want to know what its area is, the answer is that, well, I might have the wrong power, but its area is the inverse of the radius of the circle. So if the circle is large, the 2 torus shrinks, and in the limit that we decompactify, it's only there as a reminder of how to calculate tau. But when we compactify in a circle, the 2 torus becomes real and it starts to expand. And when we go to the M theory limit, it becomes big. So that's the sense in which F theory is a theory in 12 dimensions. But we went into all this because we wanted to get rid of those monodromies. So I want to write an actual formula for M that's equivalent to saying that tau has that behavior with the logarithmic singularity. So we're going to first write the equation in a slightly different way. Well, we could factor a cubic equation. So it's a double cover of the complex x-plane with 3 branch points at E1, E2, and E3. And there's also a 4th branch point at infinity. Now, the A and B cycles are the following. You could, they're not uniquely determined. I'll just give an example. An example of an A cycle is to go from E1 to E2, and then to go back on the second sheet. We can take that to be the A cycle. And an example of a B cycle is to go from E1 to E3 and then back on the second sheet. So the formula for tau, if we make that choice, is the integral. Okay. Another fact is that omega can be dx over y. That's a holomorphic differential in this version. You could ask me why it isn't just dx rather than dx over y. The answer is actually that dx has a pole at infinity. Because if you integrate from a finite point to infinity dx, you get infinity. But on the Riemann surface, infinity is at a finite distance. So the integral of omega up to infinity should be finite. So dx over y has a finite integral up to infinity. Now, if we only wanted to do that, we could take, for example, dx over x squared, but that would have poles at x equals 0. Dx over y is the one that has no pole either at infinity or anywhere else. So tau is then the integral of e1 up to e3 of dx over y over the integral from e1 to e2 of dx over y. Well, I should multiply each of them by 2 because what I wrote was the integral on the first sheet, but we have to integrate backwards on the second sheet. However, in that second half of the integral, we're going in the opposite direction, but y has the opposite sign. After all, if I take the square root, y is plus or minus the square root of x cubed plus ax plus b. So the two sheets differ exactly in the sign of y. And when we go back in the second direction, on the second sheet, we're going in the opposite direction, but y has the opposite sign. So we just get a factor of 2. So the 2's cancel out. And tau is the ratio of these integrals. Now, the formula makes it clear that tau is finite as long as e1, e2, and e3 are distinct. So the only way the tau could diverge is if two of these are equal. For example, if e1 equals e2. So if e1 goes to e2, tau goes like the logarithm of e1 minus e2. So that's going to help us write down an actual equation in which tau will have this logarithmic behavior near z equals 0. Actually, we're going to make an elementary change. Here, we shifted x so that there was no x squared term. But instead, we could have shifted x so that the equation had no term linear in x, and that'll be more convenient. So after shifting x, we'll just actually change x to x plus 1/3 so that we get y squared equals x cubed plus 1 times x squared plus stuff a tilde x plus b tilde. We're just adding 1/3 to x compared to our previous formula. And then, for the n d7 branes, well, y squared is supposed to be something where at z equals 0, two of the e's are becoming equal so as to produce the singularity. So we just take x cubed plus x squared plus z to the n. You see, if z isn't 0, for z small but not 0, this cubic polynomial on the right-hand side has distinct roots. So the e's aren't equal. But obviously, if z is 0, two of the e's are equal because the polynomial has a double root. The roots of the polynomial x cubed plus x squared are -1, 0, and 0. So at z equals 0, there's a double root. And if you work a little harder, you'll find out that, well, it looks like x squared plus z to the n equals 0. If z is very small, there are two roots where x is very small, then we can ignore the x cubed term. So we get this, and therefore e1 and e2 are plus or minus the square root of minus z to the n. So that means that the logarithm of e1 minus e2 is n times something, n times log z, times a constant. Sorry. The constant is just a half, but it's log of z over a constant. So, by putting a z to the end here, the logarithm of e1 minus e2 is proportional to n, which is going to give us the tau we want, except that it's gotten unfortunately erased, apparently, or else hidden, maybe. Anyway, the tau we wanted was the tau was supposed to be minus I n over 2 pi log z over z0. Well, you have to work out the constants to convince yourself at some point in life, but anyway, this formula has the right tau for n d7 branes. So that formula describes n d7 branes at z equals 0. Okay. Well, I wanted to do this for n d7 branes at an orientifold plane at z equals 0. I guess there was some homework I was supposed to do last night to reconcile the 4 and 8. I'm still having a little trouble. So, I've cheated slightly to get the right answer. So, well, sorry. These are n full d7 branes, which means 2 n d7s on the covering space. So, I took the monodromy to be tau going to tau, the monodromy under z going to e to the 2 pi I z. Okay. Since there's an orientifold, you could take the monodromy when you go halfway around. But I'm going to write down the monodromy if we go all the way around the z-plane. The orientifolding, remember, is z going to minus z. That's why there would be a monodromy for going halfway around. Well, I took it to be tau going to tau plus 2 pi times 2n minus 4. 2n is the contribution of 2n d7 branes on the covering space. Minus, well, there's a negative contribution to the d7 brane charge from the O7 plane. I know it's supposed to be minus 8, but we get a better answer here if we use minus 4, and I'm afraid I don't quite know why. Maybe some of you can help me. Let's do a little computation. To have this, we first write it down on the covering space. So I write down the F-theory equation that would hold if the d7 brane charge is like so, and we aren't going to divide by z going to minus z. Then we'll divide by z going to minus z. So it would be the same as I just told you. Y squared is x cubed plus x squared plus z to the 2n minus 4. Now z to minus z. And when we take z to minus z, we're supposed to take y to minus y. That's actually required by supersymmetry. I was not sure how I was going to explain that fact. It would be easier to explain if we were doing M theory. If we're doing M theory, then this complex manifold here is real. I didn't mean it was real as a real manifold. It's real in the sense that it's an honest space with a metric and everything, not just a complex structure. And supersymmetry tells us that we have to preserve the holomorphic 2 form. And the holomorphic 2 form we could take to be dx dz over y. So we get a symmetry of the space when we change the sign of z without changing the sign of y, but it would not commute with any supersymmetries because it would change the sign of omega. So the supersymmetric orientifolding operation acts as y going to minus y. So that's an explanation that involves compactifying to 7 dimensions in M theory. there is a type 2b explanation. The duality group of the SL2Z of F theory, of type 2b, I mean, sorry, is a duality transformation of the 2 torus whose tau parameter is tau. And y going to minus y corresponds to the element minus 1 of SL2Z. Minus 1 is the product of worldsheet orientation reversal and what's called minus 1 to the F left. And, well, we know that an orientifold reverses the orientation of the worldsheet. The quick answer is that y goes to minus y reflects the fact that it reverses the worldsheet orientation in string theory. So, unfortunately, this point needs a longer explanation. We have this element in SL2Z. SL2Z is the group of duality transformations, most of which are non-perturbative. But this one is perturbative. That element is omega, which orientation reversal for the worldsheet, times what's called minus 1 to the F left. You might not be sure about the minus 1 to the F left, but at least you probably know that the orientifolding reverses the string worldsheet, and therefore it includes an omega. There's an orientifold in every dimension. They all act by omega, but half of them act by minus 1 to the F left and half don't. But for the 07 plane, there's a minus 1 to the F left in there. The product, as SL2Z transformations, one of them is this, and the other is this. And their product is just minus 1 in SL2Z, the central element. And minus 1 is just the symmetry of a genus 1 Riemann surface that comes from the operation x to minus x on the x-plane. So, I mean, if you take x to minus x, it maps this fundamental domain to a different one, but then, of course, you can translate it back. So that gives a symmetry of the Riemann surface. And in terms of our using a cubic equation to describe the Riemann surface, it's y going to minus y. So the fact that we're taking y goes to minus y is because we're orientifolding to give a quicker statement. I'm a little bit afraid that what I've done is to give several explanations, each of which was explained too briefly to be convincing. But I hope at least one of them was understandable for most of you. Gosh, I've just realized something, which is that I'm running out of time. So we're going to try to be a little bit more brief now. So the way we divide by z to minus z and y to minus y is that we only consider invariant polynomials. And, well, of course, x is invariant, and the other guys are y squared, z squared, and yz. Well, we don't have to bother about y squared because the equation expresses y squared in terms of x and z. So we don't have to consider it separately, but we should consider, we'll let u be z squared and we'll let v be yz. So dividing by z2 means that we're going to get rid of x, y, and z in favor of x, u, and v. So we should find out the equation that x, u, and v obey. Well, v squared is z squared y squared, which is u y squared. And that's an equation for y squared, so that's u times x cubed plus x squared plus z to the 2n minus 4. But z to the 2n minus 4 is u to the n minus 2. So we can write this as ux cubed plus ux squared plus u to the n minus 1. So we've discovered an F-theory equation that describes an orientifold with n full D7 branes, one which has SO2n symmetry. So we've gotten the following. We found F-theory equations for two cases. For n d7s, the gauge group is supposed to be un, and the equation was y squared equals x cubed plus x squared plus z to the n. And for n d7s plus an O7, the gauge group is SO2n, and the equation was v squared equals ux cubed plus ux squared plus u to the n minus 1. So we're F-theorists. We've derived the equations that describe UN or SO2n gauge theory in F-theory. Now, not coincidentally, these equations have singularities. So let's look at this one. Well, first of all, if n is 1, un is abelian. And F-theory has no problem describing abelian gauge symmetry because there are various Ramond-Ramond fields. There are Ramond-Ramond and Neveu-Schwarz fields in type 2b. And when you compactify, some of them generate U1 gauge fields in 8 dimensions. So there's no need to explain the U1. And if we set n equals 1, there's no singularity here. In fact, let's look at the equation for n equals 1. We can just solve for z in terms of x and y. Z is y squared minus x cubed minus x squared. We solve for z so we can forget about it. It's just a function of x and y. And the space is just the xy complex 2 space with certainly no singularity. And as I said, we didn't need a singularity because the gauge group was abelian, and type 2b, or any string theory, generates abelian gauge symmetries from Ramond-Ramond and other p-form Neveu-Schwarz p-form fields. However, if n is bigger than 1, we have a non-abelian gauge theory, and there's no classical way to generate non-abelian gauge theory from type 2b. So something funny has to be going on. Something where supergravity breaks down, because supergravity is not going to give us non-abelian gauge fields out of type 2b. What breaks down is that for n bigger than 1, there's a singularity at x equals y equals z equals 0. Near the singularity, when x is small, we can ignore x cubed compared to x squared. So the singularity is y squared equals x squared plus z to the n. It's traditionally called the an minus 1 singularity. And the fact that it's related to SUN gauge symmetry, well, when it was discovered in F-theory, it wasn't a new result for the following reason. It already was known that in M-theory, the an minus 1 singularity gives SUN gauge symmetry. But F-theory on a circle gives M-theory, as I explained over here. And this complex manifold, which is described by one of these equations, comes to life in M-theory. And the M-theory is going to have an SUN singularity. So the most natural interpretation is that the F-theory had the SUN singularity before compactifying on a circle. So what we've derived is the M-theory analog of the fact that in F-theory, sorry, I got it backwards. We've derived the F-theory analog of the fact that in M-theory, the AN singularity gives SUN gauge symmetry. Now, the same idea holds true here. If n is bigger than 1, we have non-abelian gauge symmetry for the O7 plane with D7 branes. And non-abelian gauge symmetry isn't going to come from supergravity, so there's got to be a breakdown of supergravity. What makes supergravity break down is a singularity. Near the singularity is when VU and x are all 0. We can ignore ux cubed compared to ux squared because x is small. So the singularity looks like v squared equals ux squared plus u to the n minus 1. And that's called the dn singularity. And it's already known, when this calculation was first done in F theory, it was already known that the dn singularity in M theory gives SO2n gauge symmetry. dn is just a fancy name for SO2n. And so it's natural to get the same gauge symmetry in F theory, which when compactified in a circle will then give the M theory result. So this is a nice, but not totally new when it was obtained. Well, it was new in the type 2b context, but anyway, it's a nice result, but consistent with the type 2a and M theory results, that the dn singularity gives SO2n gauge symmetry. Now, there are other things which are called E6, E7, and E8 singularities. And those are known in M theory to give E6, E7, or E8 gauge symmetry. And the only reasonable, if we take M to have a E6, E7, or E8 singularity, when we compactify in a circle, we have to get E6, 7, or 8 gauge symmetry in M theory. The only reasonable interpretation is that there already was E6, E7, or E8 symmetry in F theory. So we extend our F theory repertoire slightly, and we could write down equations, except I don't remember for sure if they're in my notes. We could write down equations that give E6, E7, or E8 in F theory. Well, I can write the right one for E8. E8 comes from the equation y squared equals x cubed plus z to the 5th. And there are some other fellows that give E6 and E7. They're explicit equations, but the chance of error is too high, so I won't write them down. Now, if I had more time, but I really am running out of time, I would have wanted to spend maybe 15 minutes to just review the M theory story about why these singularities give the gauge symmetries they do. But time's winged chariot tells us to move on. Remember, we're still heading for that up-quark mass Yukawa coupling, which is supposed to arise when we do what can't happen in perturbative string theory, where two orientifold planes meet an extra D brane. So we need to do a few extra things. Yes?
What's the brane configuration?
There's no perturbative brane configuration. That's why we got as far as we could with perturbative brane configurations, and beyond that, to understand the exceptional groups. No? Sorry. If you wanted to give a brane configuration, it would involve PQ branes. So there isn't an elementary story with the brane configuration that would make what I've said simpler. There are brane configurations with PQ branes. If there were a brane, do you remember yesterday I said that we almost didn't have to do F theory? I said we could almost build up this story with D branes and O7 planes, but we couldn't quite get there. What we can't quite do is to explain with those ingredients the Yukawa coupling that will give mass to up quarks. For that, we need an E6 singularity, and I wouldn't have started talking about singularities if there was a more elementary description with branes. We could talk about PQ branes. I don't think it would have helped, though. And we're going to re-examine yesterday's story. Well, so first let's how we got matter. Well, our gut theory is based on 5 D7s. And when we intersected another D7, we got a hypermultiplet in the 5. Or, if we intersected an orientifold plane, we got a hypermultiplet in the 10. Now, either of these intersections enhance the symmetry. In the following sense. When 5 D7 branes intersect a 6th D7 brane, at that point, we have 6 D7 branes which could have had U6 symmetry. In a sense, just at that point, there's U6 symmetry, but away from that, it's broken because the branes go in different directions. And here, so at a generic point, we had U5, but it got enhanced to U6. I think it's better to call it U5 times U1. So generically, we have U5 symmetry plus a U1 on the other D7 brane. But where they meet, there's a U6 symmetry. In this case, here we have SO10 symmetry in the sense that the 5 full D7 branes meeting the orientifold plane, well, if they were all coincident, the gauge symmetry would be SO10. So where they're coincident, we think of it as being SO10. But generically, we just have U5. And the orientifold plane by itself, the bare orientifold plane, has no gauge symmetry. So it's not U5 times U1, it's just U5. Now, we already know from string constructions that we get matter fields at these intersections. But we're going to redo it from the point of view of field theory. And here we're following another paper by Vafa and Katz from about 10 years ago. More than 10 years ago. To motivate it, we'll think of these as being almost parallel. So we have another D7 that's not quite coincident with our 5 D7s, but it meets at a very small angle. So the separation is very small over a big distance. So we can treat it in field theory. And in field theory, what is the field theory? Well, if they were all coincident, we'd have, when they're coincident, we would have an 8D super Yang-Mills of U6. And the bosons are A mu, where mu runs from 1 to 8. And there are 2 scalar fields phi, or if you like, a complex scalar, in the adjoint representation. And the complex scalar phi describes the positions of the branes in the normal direction, which is what we usually call the z direction. So now if you want, the z plane is perpendicular, and these branes are at positions in z. So x mu, where mu goes from 1 to 8, describes the motion along the D7 branes, and phi of x describes the z values of the branes. So in field theory, you describe this by a field phi of x that breaks U6 to U5 times U1. Now, all this picture is happening in compactification to 6 dimensions. So it's R16. So how should I put it? Phi only depends on the last 2 x's. Because the two D7 branes are meeting on a sixth manifold, which is the six-dimensional Minkowski space where we get a hypermultiplet in the appropriate representation. So we could introduce a complex field, a complex coordinate x, which is x7 plus I x8. So phi of x is a complex function, complex adjoint valued function of a complex x. And the case we're interested in is the one that leaves u5 times u1 invariant. So phi is something like this. Okay, we could add to phi a multiple of the identity, but that would just move all our branes without breaking the symmetry, so it wouldn't be interesting. The case we're interested in, let's say that 5 of the branes remain at x equals 0, and the sixth one is displaced. And so that the matrix phi looks like this, times epsilon. Epsilon is small because we're taking the slope to be small so that we can describe this by field theory, times x minus x0, let's say, where x0 is the value of the complex x coordinate at which this is happening. So we've got a symmetry breaking from u6 to u5 times u1, and the field that's breaking the symmetry looks like a vortex. It's a complex function of a complex spatial coordinate x, and it wraps around and has a 0. It doesn't maybe look like a vortex here, but that's because I can't draw 4 dimensions. I can only draw a 2-dimensional slice. So you got to remember, a D7 brane has an 8-dimensional world volume, but they have got 6 dimensions in common. And all the fun is happening in the last 4 dimensions. Then these represent 2 manifolds inside a 4-dimensional space. And the two manifolds meet at a point. So that means that phi is 0 at x equals x0, but there's only one point where it's 0. And to get a simple 0 at x equals x0, it has to have a winding number around the 0. If it's going to be smooth. You could avoid having a winding number if it was x minus x0 times x bar minus x0 bar. Well, I think more simply I should say that phi is linear in x because these branes are straight. So if it's going to be a linear function, we don't want something like this. If we wrote real x minus real x0, that would be 0 along a real line, not an isolated point. To make it linear and have an isolated 0, it's got to just be a complex multiple of the complex coordinate x minus x0. And the complex multiple is small so that field theory is valid. That means that the branes meet at a small angle. And now what we set up is a vortex. And when we solve for the 0 mode in a vortex field, when we solve the Dirac, it's a vortex. I hope I haven't lost you and you understand it's a vortex. It's a complex field that has a 0 at x equals x0, and it winds around the 0. So now if we have a fermion coupled to the vortex, it will have a 0 mode. Well, what are the fermions coupled to the vortex? They're the interesting fermions are in the adjoint representation, and the interesting part is the part that doesn't commute with phi. So the guys that have the 0 modes are fermions that live here. They're in the part of u6 that isn't in u5 times u1. And they get a 0 mode in the vortex field, and that's the fundamental of u5. So you already knew that there's a 5 of u5 from the brane intersection, but I'm telling you a more general way to derive it, which we'll be able to use in the exceptional case in a moment, from the point of view of field theory. So any questions about it? So the fundamental 5 that arises when 5 d7s meet another d7, if the intersection, it's there regardless of the angle, but if the intersection angle is small, the phenomenon can be described in field theory, and it arises in field theory from the zero mode of a fermion in a vortex field, where the vortex field describes the symmetry breaking. The symmetry breaking is that there's a U6 symmetry where the branes intersect, reduced to U5 away from there. Now, the beauty about this description is that it's general. For example, let's now, just for practice, do 5 d7s meeting at orientifold plane. But I'll take the angle to be at a small angle. And I won't draw the mirror image this time. So the symmetry is SO10 here. And it's U5 here. And without further ado, we can describe it in field theory by the same scalar field being epsilon times a matrix that breaks SO10 to U5 and looks like this, times x minus x0. It's a vortex again, and the fermions that are charged with respect to phi will get a zero mode, and those happen to be in the 10 of SU5, or U5. So we'll get a hypermultiplet in the 10 of U5.
Why aren't we discussing the commutative, the U1?
Which other U1?
SU5 cross U1, U5 cross U1.
There isn't, in this case, there isn't another U1. Here we did discuss U5 times U1 because we did it in U6, which contains U5 times U1. Here there isn't another U1 because the orientifold doesn't support a U1. In neither case did I cheat. I always discussed the gauge group that was actually present. So the intersection of the orientifold with the d-branes supports a hypermultiplet in the 10 of U5. And from this point of view, we discover it by the zero mode in the field of a vortex. So although we won't exactly need it, I'll just briefly mention that we could do other cases. We could have, I'm not sure how to draw it. We could have the O7 plus 5 D7s. In this lectures, we've been aiming for SU5 gauge theory, but supposing we were aiming for SO10 gauge theory. Then on our surface S, we would have not just 5 D7 branes, but an O7 plane plus 5 D7 branes, supporting SO10 gauge symmetry, SO10 gauge theory. And then we'd be asking ourselves, how can we get matter fields in the 16 of SO10? Well, the answer to that question is that there's got to be a point, there's got to be some place. Okay. The picture would be like before. There's an S which now has SO10 symmetry, and it would have to intersect something where the symmetry is enhanced. And the symmetry would be enhanced here to E6. And I claim that when it's enhanced to E6, we would get a hypermultiplet in the 16 of SO10 supported there. And we would derive it in the same way. Well, first of all, what this thing is we would discover by a little bit more study of the F-theory equations. But after finding what it is, we'd make it meet us at a glancing angle so that we can use field theory. And then we'd have E6 here broken down to SO10 here. And we'd have a vortex breaking E6 down to SO10, and some fields would have zero modes, and they'd be in the 16 of SO10. And if we wanted, we could also use the same mechanism to generate 27s of E6 and 56s of E7. But time is really running out, and we want to do the 5-10-10 Yukawa coupling that I've been promising you for about a day and a half. So let's look at how that happened in our example, and then we'll formulate it in general. So we had this thing that generically had U5 symmetry. And then there was a locus where the U5 was enhanced to U6. And there was a locus, an orientifold, where it was enhanced to SO10. And there was a mirror image where it was also enhanced to U6. And where everything intersects, what did we have? Well, we had 6 D5 branes and their mirror images meeting an orientifold plane, and that would give SO12 symmetry. At the heart of everything, there's an SO12 symmetry. So if we've got the courage, we can describe this in field theory. And the field theory description is good if the angles involved are glancing. What happened, the reason I want to describe it in field theory is the following. When we understand how to describe it in field theory rather than using branes, it'll automatically carry over to the other cases. Maybe I should tell you what's the it that's supposed to carry over. The generic gauge symmetry was U5. When it gets enhanced once, we get matter. And when it gets enhanced twice, we get a Yukawa coupling. And magically, when the symmetry gets enhanced twice, 3 curves all meet there, so that 3 fields can participate in that Yukawa coupling. So there is a dual picture that gives the other Yukawa coupling. The dual picture, it's the same picture except 2 dotted lines and 1 solid line instead of 1 dotted line and 2 solid lines. So here's what perturbatively would involve SO10. Generic is U5. And here's another orientifold plane. They really can only be treated as orientifold planes away from where they meet each other. In weak coupling, orientifolds can't meet. So at that intersection, you have to use F theory. Then there's this other guy that enhances to U6. And where they all meet each other, the symmetry is enhanced to a group that contains both SO10 and U6. And the answer is that that group is E6. And that's really why we need to do to learn some F theory. E6 is an exceptional group, so we can't describe E6 symmetry just with branes in an elementary way. There was an answer. The question was asked, and there's an answer, but it's not a very helpful answer. F theory is more useful. So if we get a field theory explanation of why this generates a Yukawa coupling, the same reasoning carries over to show why this generates a Yukawa coupling. So I'm going to see how close I can come to doing that in 5 minutes, let's say. And we'll finish up with that, I guess. So suppose we're planning, okay, in this example, we'd be breaking SO12 to U5. So remember, we deform this so that all angles are small, and therefore we can use field theory. And so in field theory, the symmetry breaking is by a complex Higgs scalar field phi. The complex Higgs scalar field phi will now be a function of 2 complex variables because we're now using all 4 dimensions of S. Each of these surfaces go off in different directions. You'll see why in a second. So I write down the most general form of phi that leaves U5 times U1 unbroken. And it's like this. That's the most general element of the adjoint representation of SO12 that leaves unbroken SU5 times U1. And we're going to actually think of A and B as complex coordinates on S. S is four-dimensional, so we can describe S by two complex coordinates that I will call A and B. And I claim that the configuration we want is completely generic in the sense that every Higgs field that breaks SO12 to U5 occurs exactly once. And now I want to show you that that gives the right picture, which kind of, I hope, will look like magic. I think it's kind of magical. There are three funny spots. So if B equals 0, we get an enhancement to U1 times SO10. So this here is B equals 0. And there are two other places where something funny happens. If A equals B, we get U6. And that's kind of obvious. But you might have to think for a second to realize that if A equals minus B, you also get U6. Because A equals minus B is the same as A equals B up to a reflection of one of the coordinates in the 12 space that SO12 acts on. So these guys are A equals B and A equals minus B. So we've gotten a description of that whole complicated thing in field theory. And it seemed like a bit of a coincidence that two surfaces meet at one point, but we've given a field theory explanation. It's not our fault. We just wrote down the general ansatz breaking SO12 to U5 times U1. And there are three different conditions that lead to enhanced gauge symmetry. One will support a 10 because it has SO10, and two will support 5s because they have U6. And everything is happening inside SO12, so all the fermion zero modes are just zero modes of an SO12 gauge theory in 4 dimensions. And from the string theory, we know that there's a Yukawa coupling. But what it means in field theory is that the 3 zero modes on the 3 vortices overlap in such a way that they have a non-zero Yukawa coupling. Well, this picture can be described in field theory the same way. And this is how I will conclude. In this case, we're supposed to break generically E6 to what? No, well, we have to remember some U1s. That's what I'm worried about. U5 times U1, I guess. I have this neatly written down, and I really want to find it. Okay. So E6 contains SU6 times SU2, which in turn contains SU5 times U1 in SU6, and another U1 in SU2. And the most general Higgs field that is going to leave U5 times U1 unbroken lives in these two guys. So again, there are two complex parameters in the symmetry breaking, and we take those as simply the coordinates. We're trying to find a field theory description of this picture. We take those as being the coordinates of S. So we take phi to be A times U1, let's call it 1 and 2, plus B times U1, 2. And I claim that as you vary A and B, there are 3 places where there is enhancement. So it's obvious that B equals 0. A equals 0 leads to enhancement to SU6 times U1. Because A is the one that breaks SU6. And we're supposed to find a single enhancement to SU6. But we're supposed to find 2 enhancements to SO10. That's why I've got my trusty notes here. because we might have had trouble getting that one on the fly. The adjoint of SO10 is 78, which is under SU6 times SU2. This is SU6 times SU2. And if I go down to SU5 times SU2, then the 22 is 10-2 plus 10 bar 2. So we have two copies of 10 plus 10 bar. And if one of them is massless, we're going to get an enhancement to SO10. Well, there are two 10s, and they have the same charge under A, but they have opposite charges under B, which is in SU2. So there are two different conditions which will make one or the other 10 massless, and those give us our two enhancements to SO10. So roughly, B equals plus or minus A gives enhancement to SO10. Actually, SO10 times U1. So this is the field theory picture of this thing that isn't accessible in perturbative string theory that describes the 5-10-10 Yukawa coupling. Well, I think I'd better stop so that we can have a decent break and time for the next speaker. I would have just mopped up a little bit by drawing a few pictures of what the whole thing looks like to get all the Yukawa couplings we want and don't want. But I think it's better to stop here. Yes? Well, yes. Well, they discussed a lot of scenarios involving it. I can't see what to say quickly, though. I can't see what to say quickly beyond what he said, right?
It was just that it's possible to do an essay, a singlet.
Yes. That statement is correct, certainly. Okay. So we're not worse off. We can arrange to have no suppression beyond the usual story. There's a Higgs-Higgs singlet coupling, and we have to get a lucky VEV for the singlet eventually. That's one way to approach it. In the paper, they discussed a lot of things, but I won't try to say anything now.